Welcome to AI Paper Slop. What if I told you that your models already know the perfect answer, like 98% of the time, but your evaluation system is it's just too blind to see it?
Yeah, it's a pretty wild thought,
It
honestly.
really is. So today we're dissecting this massive paper from researchers at Stanford, UC Berkeley, and NVIDIA. It's titled LLM-as-a-Verifier, a general-purpose verification framework.
Right.
And if you are building agents, you know that scaling test time compute is basically the new frontier. But standard LLM as a judge methods are completely bottlenecked
Yeah, they really are.
because they take these incredibly rich, nuanced probabilistic distributions from the model, and they just collapse them into these really coarse discrete scores, which of course inevitably leads to massive tie rates.
Exactly. You lose all the signal in the rounding.
Right. But this paper introduces a fix. By computing the mathematical expectation over the distribution of scoring token logits, they generate this continuous, really fine-grained reward signal.
Which is huge.
It is. And they use this to unlock 3 distinct axes of verification scaling. So that's score granularity, repeated evaluations, and criteria decomposition.
Yeah.
And then you pair that with this O of NK ranking algorithm they call the probabilistic pivot tournament. And suddenly this zero-shot framework it achieves state-of-the-art across distributed bench verified, terminal bench V2, and even multiple robotic control benchmarks.
Yeah, the magnitude of this shift, it really comes from addressing what we call the headroom problem.
Okay, unpack that a bit.
So we spend immense resources optimizing the generation side of the equation, right? Like making sure the model can output the right code. But verification, which is the ability to reliably determine the correctness of a really complex trajectory that is lagging way behind.
Right, because generating is one thing, but grading it is another.
Exactly. Take terminal bench V2 as the prime example. If you generate, say, 100 trajectories per task and you employ an oracle pass at K.
Meaning you assume an omniscient grader that perfectly selects the best trajectory from the pool every single time.
Right. If you have that perfect oracle, the success rate actually hits 98.9%.
Oh, wow. So the raw capability is already baked into the weights. Like if you give the model enough sampling budget, the correct sequence of actions is quite literally sitting right there in the output pool.
Yes, it's there. We fundamentally suck at picking it out of the lineup.
That is so frustrating. So why are we so bad at it?
Well, the failure mechanism really comes down to how we force these models to render judgments in the first place. The paper highlights this brilliant case study on a query-optimized SQL task.
Okay.
So the agent's goal is to take a slow SQL query and write an optimized version that yields the exact same output. And the evaluation pool has 2 candidate trajectories.
Got it. 2 options to grade.
Right. So the successful one, it actually runs the original query on the canonical database, waits the 5 minutes for execution, and then runs a strict diff against the new query.
Proper methodology.
Exactly. But the failing trajectory tried to game the system entirely. It builds a brand new index database copy, runs the query there, and compares the outputs.
Wait, really? It fakes it.
Basically, yeah.
Yeah.
And that is methodologically flawed because, sorting behavior and indexing can fundamentally alter the output state.
Okay, so one does the work, the other takes a sketchy shortcut. And when they feed those 2 trajectories into Gemini 2.5 Flash to act as a judge, what happens?
Well, the model actually detects the anomaly. If you look at the internal reasoning trace, it shows the model explicitly recognizing that creating a new index database is a shortcut.
Okay, so it knows.
It knows. But because the shortcut still produced a superficially correct answer, the model expresses its preference using this really highly hedged language. Like, it calls the valid trajectory, quote, marginally more direct.
Marginally more direct, but here's the catch, right? When you force that nuanced, hedged reasoning into a rigid prompt that asks for a discrete score on like a 1 to 5 scale.
The model has to make a hard rounding decision.
Right.
And because it views the indexing shortcut as a relatively minor infraction, it just assigns both trajectories a 5. And over 100 repeated runs of this exact prompt, the discrete judge spat out a 5-to-5 tie 88% of the time.
88%.
Yeah. The critical verification signal, that marginal preference for the rigorous approach, it's completely annihilated by the rounding function.
It's like, okay, if you're an ML engineer managing a team, think about this like a code review, right? You have one pull request that is absolutely flawless, and another that technically passes the tests but has a slightly sketchy workaround.
Yeah, that's a perfect analogy.
If your version control system only allows a binary approve or reject button, you're forced to click approve on both. The system just throws away your internal confidence level.
Exactly.
So the central question of this paper is, how do we bypass that binary button? How do we extract and actually scale the model's probabilistic confidence?
Right, and they approach this through 3 scaling axes. So starting with granularity.
Okay, break that down for us.
The standard method just takes the argmax token, so the single highest probability discrete scorer token. But this new framework, instead, calculates the mathematical expectation over the logits of multiple score tokens.
Meaning what, exactly, in practice?
Meaning, if you expand your prompt's grading scale to, say, a 20-point system, you extract the raw probability the model assigns to each of those 20 tokens, multiply each probability by the token's scalar value, and sum them all up.
Oh, I see. Which projects the model's internal belief onto a continuous, highly sensitive spectrum. So a 5-to-5 tie in a discrete system might actually resolve to like a 4.92 versus a 4.81 in this continuous expectation.
Exactly. What's fascinating here is the math behind why this improves performance without a single extra inference pass.
Wait, really? No extra compute for that?
None. It's rooted in the signal-to-noise ratio, or SNR. In this context, SNR is defined as the expected score gap between the good and bad trajectories, divided by the variance of that gap.
Okay, follow.
So when you increase the score granularity from just 1 token to 20 tokens, the SNR mathematically jumps from 0.775 up to 0.799.
Wow.
Yeah, you are perfectly calibrating the score separation. You're essentially just squeezing more juice out of the forward pass you already paid for.
Okay, here's where it gets really interesting, though. Extracting expected logits across 20 tokens gives us this beautiful continuous score, sure, but we are still relying on a single forward pass.
Right.
So if the model hallucinates or, gets sidetracked by some weird prompt artifact on that specific run, your continuous score is basically just precisely calibrated noise.
Yeah, that's the vulnerability, and that's why granularity has to be paired with their second axis, which is repeated evaluation.
Monte Carlo averaging, right.
Exactly. They use Monte Carlo averaging over K-runs. So by running the verifier, say, 16 times and averaging those continuous scores, you drastically shrink the variance.
Makes sense. Law of large numbers.
Right. But there is an important caveat here for anyone deploying this. The returns diminish on a logarithmic curve.
Okay, meaning?
Meaning those first few repetitions give you a massive variance reduction. But as K scales higher, you start hitting the model's correlated biases on truly hard problems. Like, if the model fundamentally misunderstands a niche API call in the code, running it 64 times isn't going to fix the underlying blind spot. It'll just confidently give you the wrong score 64 times.
Right. Which brings us, I assume, to the third axis, criteria decomposition, which seems specifically designed to tackle those exact blind spots.
Yes, exactly.
So instead of prompting the verifier with this monolithic question like, is this long horizon trajectory correct? They mathematically split the verification. So for a coding task, they evaluate specification, output, and errors separately.
Right, and decomposing the criteria prevents the model's attention mechanism from being hijacked by a single salient feature.
Oh, like when it hyperfixates on something minor?
Exactly. In a complex compound prompt, an LLM will often fixate on, say, a glaring syntax error and just completely ignore that the underlying logic of the algorithm is fundamentally backward.
Right, right.
By forcing isolated probabilistic evaluations across distinct criteria, you ensure the final aggregated score reflects the entirety of the trajectory.
Okay, but let me push back a little here. Does expanding this grading scale and running Monte Carlo repetitions actually grant the verifier new reasoning capabilities? Like if we give it a 20-token scale, does it suddenly understand a Python script it previously couldn't?
That's a great question, but no. The underlying intelligence of the model remains totally static. Enlarging the ordered token set doesn't grant the verifier new parametric knowledge about the code.
So what's actually happening?
What it does is provide the decoder a much finer space to express itself. Nearby beliefs that a discrete prompt would have just crushed together into a single integer are now allowed to mathematically separate into distinct rewards. We aren't making the model smarter, we're just removing the artificial bottleneck that was dumbing down its output.
Okay, that makes perfect sense. The math is undeniably elegant, but, and this is a big but, if you're actually putting this into a production environment, you hit a massive wall with API costs.
Oh, absolutely.
Because if I have n candidate trajectories and I want to find the absolute best one using pairwise comparisons, a naive round-robin tournament requires O of n squared inferences.
Right, which is brutal.
Yeah. If n is 20, you are looking at nearly 200 verifications just to grade a single task. The cloud compute bill for that at scale would be completely unjustifiable. So how do they solve the tractability problem?
The computational fix is this specialized ranking algorithm they designed called the Probabilistic Pivot Tournament, or PPT.
Okay.
It drops the complexity from O of n squared down to O of nk, where k is a small, fixed number of pivots. And they execute this in 3 distinct phases.
Let's walk through them.
Phase 1 is the ring pass. You arrange all n candidate trajectories into a random Hamiltonian cycle.
Okay, so for those a bit rusty on graph theory, a Hamiltonian cycle is a closed loop in a graph where every single candidate acts as a vertex and is visited exactly once.
Right, so you score adjacent pairs in this circle. Every candidate acts as candidate A in the prompt exactly once, and candidate B exactly once.
And why do it in a circle like that?
The mechanism here is designed specifically to neutralize positional bias. LLMs heavily anchor to whichever text appears first in their context window.
Oh, right, the first is best bias.
Exactly. If you just pair them randomly, the ones that happen to be placed first get an artificial score bump. By forcing a Hamiltonian cycle, every candidate occupies both the first and second position across the ring, meaning the positional bias mathematically averages out to 0 in expectation.
That is so smart. Okay, so once that ring pass is complete, you basically have a rough, unbiased baseline score for every candidate, and it only costs you n inferences.
Correct. And from there, you move to phase 2 and 3, which are pivot selection and the actual tournament. You rank the candidates based on that initial ring pass, and you extract the top K candidates, say the top 4 or 5.
Those are your pivots.
Those are your pivots. You discard the round-robin concept entirely. You only spend your remaining compute budget comparing the remaining non-pivots against these top seeds.
Okay, I see where this is going.
And finally, you use a Bradley-Terry preference model to aggregate the wins and losses into a final ranking.
Right, and the Bradley-Terry model is crucial here because it doesn't just rank them cleanly from 1 to n based on win counts. It converts those head-to-head win ratios into a continuous latent strength rating.
Exactly.
So if candidate A beats B and B beats C, Bradley-Terry calculates the exact probabilistic distance between them based on the margins of victory. This tournament structure, honestly, it reminds me of a seeded Swiss system bracket in sports.
Yeah, that's a good way to look at it.
Instead of a massive round robin where the worst team wastes everyone's time playing the second worst team, we do a quick preliminary laugh to find the contenders and focus our budget there.
It functions very similarly to a Swiss system, but with a mathematical difference tailored for machine learning. Because in human sports, you kind of assume the field is relatively competitive.
Usually, yeah.
But in agentic workflows, LLMs will often generate absolute garbage alongside moments of pure brilliance. So the ring pass isn't just about seeding. It is specifically designed to flush the garbage efficiently before the expensive part of the tournament begins.
You stop wasting API calls asking the model to compare 2 completely broken Python scripts.
Exactly. And because the final Bradley-Terry calculation normalizes the scores by the number of comparisons each candidate participated in, the pivots don't receive an inflated score just because they played more matches.
That's incredibly elegant. Okay, so this O of NK algorithm paired with continuous logit expectations looks great on paper, but the real test is how it performs in the wild.
Right, the benchmarks.
On Terminal Bench V2, using the baseline GPT 5.5 model, the discrete judge scored 84.7%. Applying this verification framework pushed it to 86.5. SWE Bench Verified saw a jump to 78.2%. But the most interesting one for me was Med Agent Bench, which simulates highly complex electronic health records.
Yeah, the MedAgent bench results really demonstrate why probability matters in safety-critical domains.
Yeah.
Consider a simulated scenario where an agent has to prescribe a medication based on a patient's dense medical history.
High stakes.
Very. Trajectory A gives the perfect drug. Trajectory B gives the right drug, but slightly miscalculates the dosage timing. A discrete verifier will often round both of them up to a perfect score because neither triggered a catastrophic drug interaction.
Right, they both technically worked.
But when you extract the probabilistic logits, trajectory B will skew slightly lower. The continuous score catches that subtle timing error that the discrete score just aggressively smoothed over.
Which is life or death in a medical context.
Exactly. And that granular sensitivity pushed Claude Opus 4.8 from 70.2% to 73.3% on that benchmark.
Okay, but you just mentioned GPT 5.5 and Claude Opus 4.8, which brings up a massive technical hurdle. The state-of-the-art frontier models right now are entirely closed APIs.
Oh, yeah. This is the elephant in the room.
OpenAI and Anthropic actively hide their token-level log probs from developers. You literally cannot calculate a mathematical expectation over the logits natively because they just refuse to expose the underlying probability distribution. So how on earth did the researchers manage to squeeze this framework out of closed weights?
It's so clever. They architected a two-stage workaround that effectively separates the reasoning from the scoring.
Okay, how does that work?
So stage one relies on the closed model. You prompt GPT 5.5 with the trajectories and ask it to generate a highly detailed reasoning block analyzing the pros and cons of both.
But you don't ask for a score.
Exactly. You do not ask it for a score. Then stage two takes the original task, the candidate trajectories, and that exact reasoning block generated by GPT 5.5 and passes the entire package into an open weights model, like Gemini 2.5 Flash.
Oh.
Yeah. You use the open model exclusively to extract the calibrated log probs for the final scoring tokens.
That is brilliant. So you're using the closed model as the brain to do the heavy domain-specific deduction, but you're using the open model as the mouthpiece to actually deliver the probabilistic score.
Exactly. And it reveals a profound insight into how we allocate compute. We're decoupling the heavy lifting of domain-specific reasoning from probabilistic calibration.
Because the open models are good enough to calibrate if they have the reasoning spelled out for them.
Right. Massive closed frontier models shine at parsing complex context, but open models are perfectly capable of reading that parsed context and providing cheap, transparent calibration. Yeah. At a budget of just a single run, so k equals 1 routing the GPT 5.5 reasoning through Gemini 2.5, Flash actually recovered a 5.2-point accuracy gain over directly using GPT 5.5 integer scores.
It beat the closed model's own discrete scores.
Yep, and it completely eliminated the 10.9% tie rate.
That is wild. Okay, so if you are an ML engineer, test time scaling for inference is great for benchmarks, obviously. But the true holy grail is using these dense verification signals to improve the reinforcement learning of the models themselves.
Well, right, entirely. That's the end game.
We want to use this mathematically smooth signal as a reward function. So what happens when you plug this continuous verifier into an RL pipeline?
It completely alters the mechanics of tracking progress and shaping rewards. And to understand why, you have to look at value order correlation, or VOC.
VOC, right.
This metric measures how well a verifier score correlates with the chronological step-by-step progress of an agent navigating a task. A robust verifier should output monotonically increasing scores as an agent gets closer to the goal state.
Meaning the score goes up smoothly the closer you get.
Exactly. When they tested this on Robert Ward bench, the LLM-as-a-Verifier hit a VOC of 0.966.
Wow. Compare that to prior discrete reward models, which tend to just saturate at 1.0 almost immediately. Once a discrete model decides a trajectory looks vaguely correct, it just flatlines.
Right. It's useless for tracking intermediate progress.
Yeah. If you are training an agent, you have absolutely no idea if step 15 is actually mathematically better than step 5 because the reward signal is just this flat block of 100%.
But the continuous expectation preserves a smooth, chronologically aligned gradient throughout the episode. And that smooth gradient is the lifeblood of reinforcement learning.
Right.
They deployed this in off-policy RL for robotics, specifically using the DSRL-SIC algorithm that's soft actor critic, with dense rewards on the Libero benchmark.
Okay, robotics. That's a tough domain.
It is, because in robotics, sparse rewards, like giving a 1 for success and a 0 for failure, are notoriously inefficient. The agent essentially wanders aimlessly until it accidentally succeeds.
Right, it doesn't know it's getting warmer.
Exactly. By taking the continuous verifier score and injecting it as a dense intermediate reward, they provided a shaped gradient pointing toward the goal. And this yielded 1.8 times higher sample efficiency compared to sparse rewards.
Achieving nearly double the sample efficiency in robotics is a massive cost saver, considering how expensive physical or simulated data collection is. But robotic manipulation is very different from, say, complex reasoning. Did they test this continuous reward signal on mathematical logic?
They did. Yes, they tested it on policy RL, utilizing GRPO group relative policy optimization to fine-tune a Quen 3.8b model on the math benchmark.
Okay, GRPO has been everywhere lately.
Yeah, and GRPO works by sampling a group of responses to a prompt and estimating the advantage of each response relative to the group average. But the critical failure mode of GRPO occurs early in training.
Because it's bad at math initially.
Exactly. When a model is first learning complex math, it is incredibly common for a batch of, say, 8 sampled answers to all be completely mathematically incorrect.
And if every answer in the sample group is wrong, the relative advantage calculation just collapses. You get a gradient of 0.
Right. The model's weights don't update because the discrete judge just outputs a wall of zeros, giving the optimizer no indication of which quote-unquote wrong answer actually contains slightly better logical steps.
So how does the continuous framework fix that?
It mitigates the zero gradient problem by running the probabilistic Piggott tournament on the intermediate reasoning traces themselves.
Oh, not just the final answer.
Right. Instead of just grading the final output, the verifier assigns a normalized preference score to the step-by-step logic. It captures fine-grained differences in reasoning quality, identifying that, hey, one trajectory correctly applied a derivative before failing the arithmetic, while another just failed entirely.
That is so powerful.
Yeah, and incorporating this dense reasoning reward yielded a 10% reduction in the optimizer steps required to reach matched accuracy on the math benchmark.
Incredible. So if we step back and look at the trajectory of the field, we are effectively using test time compute to generate automated high-fidelity reward shaping for RL algorithms.
Basically, yeah.
Like, we used to spend months manually engineering dense reward functions for robotics or math. Now we just write a comprehensive verifier prompt, expand the granularity to 20 tokens, calculate the expectation, and just let the model mathematically grade its own intermediate steps.
Well, the human element doesn't disappear, it abstracts upward.
Fair point.
Instead of handcrafting reward functions state by state, engineers are now handcrafting the verification criteria. You design the rubric, the strict guidelines for specification, output, and error handling.
And the model handles the rest.
Right. The LLM-as-a-Verifier framework takes that human-designed rubric and mathematically smooths it out into a dense, usable gradient for the RL algorithm to consume. It is a profound force multiplier for alignment because it functions entirely zero-shot across domains without requiring any domain-specific fine-tuning of the verifier itself.
We are definitively moving from LLM as a judge to LLM as a verifier. We're no longer forcing these hyper-complex, multidimensional models to truncate their intelligence into a single reductive integer.
It's about time.
Truly. But I want to leave you with a final thought on where this hardware-software convergence is heading next. If we can optimize this verifier mathematically by tuning the number of Monte Carlo repetitions and the score granularity, what happens when models become agentic enough to dynamically route their own verification budget?
Oh, that's a fascinating idea.
Right. Imagine a SWE agent working on a massive backend migration. It generates a potential code block and checks its own internal logit distribution. If the distribution is flat, meaning the model is mathematically uncertain, and the signal-to-noise ratio is low, the agent dynamically decides on the fly to increase its score granularity to 20 tokens and spin up 32 Monte Carlo repetitions to rigorously evaluate itself.
Self-regulating compute.
Exactly. But if the logit distribution is incredibly sharp and confident, it relies on a single pass, saving you the API cost. We are looking at a near future where agents self-regulate their compute spend based purely on the mathematical shape of their own uncertainty.
That would be a game changer for deployment costs.
It really would. We are finally throwing away the blunt evaluation tools of the past and giving these models the high-resolution canvas they need to actually communicate what they know.
Yep.
Well, thanks for joining us for this analysis on AI paper slop. We'll catch you next time.